Welcome back, folks. So this is part 2 of chapter 2, where we're going to pick up where we left off. We created a do file using the GSS 2016 data. We tabulated the father's degree, mother's degree, looked at missing data on those, recoded, or rather created a new variable and recoded it, and then assigned value labels to the recodes. So now we're going to do Chapter 2, Part 2, which is Graphical Representations, basically visualizing your data so that you can explore it and better understand the data distribution. So we've talked about the importance of understanding not only what the central tendency is, that is the mean and the averages in the data, but also looking at the distribution of a variable and how far away from the mean data points are. This requires you to understand your level of measurement of your variables. I hinted at the importance of that earlier, because the program sometimes won't tell you if you're trying to do something that doesn't make sense. So I will give you the example of using this tabulate command, which we used to, I'll run it again here by highlighting, we used to look at the frequency distribution of this father's highest degree, which is an ordinal variable. We can consider it an ordinal variable. It's really categories: less than high school, junior college, bachelor, and graduate. And this frequency distribution will tell us what percentage of our respondents reported each of these categories. That's helpful information. What's not helpful is trying to get the mean of this variable, for example. The program won't give me an error. It will give me a mean for father's highest degree. But what does a mean of 1.2 mean in this case, right? How do you interpret that? You don't. This is not an appropriate command to run when you have categorical data. When you have this type of data, you want to use tabulate and look at the frequency distribution. So there are certain things that the program will technically allow you to do, but you as the statistician need to know what level of measurement each of your variables are in order to know what's an appropriate summary statistic or analysis to use on that variable. This is going to come up over and over throughout the semester. How to choose the right analysis? Well, you need to know what type of variable you have. Okay, so that being said, let's take a look at some of the visualizations of different data that we have here. So we're going to start with a pie chart of this mother's degree recode. So we have this table that gives us a 0, 1, 2 for mother's degree, but let's say we want to see what percentage in a pie chart, what sort of slice of the pie are people with a high school or less. Visuals are often better ways to understand our data than just looking at a table. So we'll create this pie chart by using the command graph pie, and we're telling it what variable over this mother's educational attainment recoded variable. And we're going to tell it that the label we want to add is the percent for each pie slice, right? As opposed to, for example, the N. All right, and what did I do incorrectly here? I missed a space. So notice that it gave me a red error in the results window, invalid pie number in P label, comma, all percent. Ah, that's because, what did I miss here? It should have been all with space and then percent. So let's try to rerun it and re-execute. Sometimes it's hard to identify why something didn't work the way you expected it to. And that's where careful Googling comes in, making sure that you don't have any spelling errors in your syntax. looking back to the Getting Started do file. You have various options for help, and you should exhaust those, because the best way to learn how to do this stuff is to troubleshoot yourself. Once you've done it once and you troubleshoot yourself, you'll be far more likely to remember it. And that's what happens in the workplace when you're doing this type of data analysis. You're not going to have anyone to sort of step you through and identify the problems in your code. It's super frustrating. This happens in research all the time. All right, so here's what the pie chart looks like, and we see that nearly 80% of respondents report that their mother has high school education or less. 5% report that she has some college education, and 16% report that she has a bachelor's degree or higher. So let's look at the percentages here and compare to what we had when we ran our tabulation. So the percentages for our pie chart, 78%, 5.4%, and 16.42% match the 012 code, but we know that that didn't contain all of the respondents, right? We had people that were missing, so we want to look back at this percentage, including the missing data, and see whether this looks a little bit different when we include the missing data. So the percentages are different, right? 78% of respondents who responded to the question reported that their mothers had a high school or less education, but only 72% of all survey respondents reported high school or less. So that's taking into account the fact that 200 people didn't respond to this at all. All right, so let's do the same for father's educational attainment. I'm just going to copy this to make it easier. Graph pi over PA degree DEG. Sorry, we're going to do a bar chart rather than a pie chart, and therefore we don't need this label. So let's see what a bar chart for the father's educational attainment looks like. Okay, so again, this is the same data that we see in these tables, but far nicer for data presentation, and it gives you a sense of what the distribution looks like. And here's a case where we might collapse this junior college category wherever it makes sense substantively, often with the less than high school and high school group and only some college. And we generally distinguish college graduates from these folks because there are so few that report a junior college education. Okay, so we may want to look at what's called a histogram for age variable. This one's a little bit different because age is in fact a continuous variable. So far we've worked with these two categorical or ordinal variables, and here we have age, which we actually can use the summarize command on. So if we summarize age, we'll see that the respondents range from 18 to 89 years old. In some cases, surveys will be what's called top coded for the age category, meaning if there are people older than 80 or 89, they'll still be coded as 89 because there's so few of them. So that's something that we don't actually know if this 89 is the full value. We would have to look at the survey data description or the code book to know whether this represents top coded data or whether people actually only went up to age 89 in the data set. And the criterion for inclusion in the sample was a minimum age of 18, so it's not surprising that people range from 18 and older in the sample. Average or mean age is 49 years old, and with a standard deviation of 17.7 years. So we'll get into this a little bit later in the semester, but one of the things that you'll learn about data distributions is that 68% of people will fall within one standard deviation of the mean. And I'm just going to do a quick display command here that will allow us to calculate what that range would be. So we could calculate what the range would be for one standard deviation distance above and below the mean. You can make a command appear quickly in the window by just pressing page up or page down, and it will call up the previous command with page up and the subsequent command with page down. So here I'm taking the mean and I'm adding one standard deviation to give us the range, the top range, so it's approximately 67 years old, and the bottom of this range is approximately 30 years old. And so we can say that 68% will fall between 31 years of age and approximately 67 years of age. That's a little bit of a digression, but a little taste of what's to come in subsequent chapters. Okay, so here let's do a histogram. Oh, let me go back into the do file now. For a continuous variable, we can create a histogram, and we'll want to give the percentage of people that fall into each of the bins in the histogram. So here we have the percentage of people who fall into each of these age ranges. Well, it's hard to see what the age ranges are on the actual graph, but here it tells us what the bins are, and the width being the number of years. So we have approximately 2-year intervals here. And then we see approximately 2.5% of our data fall between 18 and 20 years old. Between 20 and 22 years old, we have almost 30%, and so on. We can get this same information by tabulating age, which you generally wouldn't want to do, because as you can see, there are so many different categories for age that it doesn't really make sense to look here and go, oh, okay, we have approximately 2%, right, cumulatively, who are age 20 or less, or age 20 to 30, we'd have to add up these categories, right? So this is cumbersome. We don't use tabulate command on data, but the histogram gives us a better summary essentially of what this is. It gives us a visual summary of the data distribution. However, in 2-year intervals, it's not very smoothed. So this curve isn't very smooth, and so if we wanted to see what the data distribution looks like, we might want to lump some of these years together. Instead of 2-year intervals, we might do something like 5-year intervals to make it a little bit, 5 to 7 years, to make it a little bit more interpretable. So let's rerun the histogram, and we're going to this time tell it that we want the bins to be larger intervals. So instead of 34 bins, these, if we counted these lines, there's 34 of them, we're going to ask Stata to give us only 10, a graph with only 10 bins, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and these represent approximately 7-year intervals, so age 18 to whatever that is, 25, and so on. And now you can see that that's smoothed out. If we were to draw a curve over this distribution, it smoothed out the distribution a bit. which makes it a little bit easier to interpret what this looks like, what the data distribution looks like. All right, so now we know what the age distribution of respondents in the general social survey looks like. We learned that you can use tabulate on this continuous variable, but it's a terrible idea. Histograms are much better to visualize that. What we want to do on ratio and interval variables is use summarize. We can use bar graphs to show these frequency distributions. We learned how to recode variables, how to always include the MI, the missing option, on tabulate so that we can see how many people didn't respond to a particular question. And we talked about why that might be. So let me just quickly pull up the sample that we talked about. Sometimes people will be coded, they're all missing, but they'll be coded in different ways. So refuse to answer is like, I don't want to answer that question. Or someone might say, I'm not really sure. Both of those are missing a response. So in this case, for example, self-placement on the ideological scale on a scale of 1 to 7. So some people could say, I don't want to tell you. Other people say, I don't really know. Other people say, I didn't take the time to think about it. All of these are still missing. So the 0.7% plus 0.3%, that's 1%, plus 7.6% of people who haven't thought much about it, totals to, well, with rounding error, 8.6, 8.7% of people. So actually, almost 10% of people are missing on this particular item. And that's what we want to know. In Stata, those people are generally coded with a period to indicate that they're missing. But sometimes you might have variables where these categories are assigned numbers. So refused might be 98. Don't know might be 99. Haven't thought much about it might be 999. But all of those we would want to, in most cases, we would want to include to tell Stata recode 98, 99, 999 to be missing, which is this variable. Or rather, this denotation. Okay, so we're looking back here. You can feel pretty good and productive about what you've accomplished in Chapter 2. The last thing that we want to do is save our do file. And we can save this as our Chapter 2 do file. I'm going to replace the one that I already worked on. The other thing that you might want to do, since we created a new variable and created labels for that variable, we could save the data set by going to Save As. I always like to save the data set with a new name using Save As so that I can distinguish the variables that I have edited. I usually like to use an underscore edited to make it easy for me to identify that that is a data set, no longer the original data set. And that is a convention that allows me to then go back to the original data set. If anything goes wrong or I code something incorrectly and I don't catch it in time and I'm worried that maybe there are other errors in the data set, it's always good to have the original data set saved separately. So we've saved our do file for Chapter 2 that has all the code that we just went through. We saved the data set. You can see that it changed the name up here as GSS 2016 underscore edited so that I know that I made changes to this. I saved it in the 318 folder that I created, so I always want to make sure I know where I'm saving my data. It seems very basic, but I sometimes get confused and maybe have a default folder open and I'm not paying attention. So try to pay attention to that. Oh, and one last thing that I happened to notice as we were chatting here and wrapping up. Indeed, this 89, luckily they have a value label on it, indicates not just people who are 89, but 89 and anyone who is older than that. So it is, this variable is top coded. That's referring back to what we were talking about with interval or ratio variables, and specifically with age, this is something you'll come across in most data sets. Okay, thank you so much for your time. We can close out of the do file, close out of Stata, and see you next time.